So a theta will be equal to 0. And let me rewrite what is theta. And theta is r theta double dot plus 2 r dot theta dot here. For this is in particular for a two-body problem. Okay. So what this means, we can do a little bit more derivations and how can we utilize this one? If I would confine you in a small room for 10 minutes, you'll come up with a good answer for me. And that is the way that people did it, and a lot of the mathematicians, they just sit down and then do something fancy, good one. So let me do the upside down, the reverse the process. Okay, so say if we do this d dt, we see what happens. Okay, let me see what happens about this one. So basically this one and this one is, we take the chain rules. So that is, the first one is 2r dot theta dot. So basically I apply the chain rule to the first term first, and then apply the chain rule to the second terms. So theta double dot, right? Okay, so basically this one is r times 2r dot theta dot plus r theta double dot, right? So basically here, let me do this one. You can see from here, let me say 0 equal to, let me multiply r to that equations. So that won't affect the it's 0 result, right? So but here you compare to this one, basically this is equal to d dt r squared theta dot, right? So I told you I kind of reversed the upside down the result here. Okay, so people played around, they found that can be equal to that one. So this one is very useful. So that means the r squared theta dot equal to constant. And what this means, let me show you certain geometries here. So this is the mass 1, and this is the mass 2. So this could be, say, imagine this is Earth, and this is satellites. Okay, and here is the distance r. And what is theta? Again, based upon this one, basically theta is this. We take this one as the center. This one is moving in orbit, so say to next moment. Let me call this small angle is d theta. So roughly, if the d theta keep it very small, so basically the distance here is r times d theta. Okay, so basically here in the very small advancement, this triangle has the area equal to 1/2 times r squared d theta. Okay, and so how can we correlate the two informations together? So basically this one, let me rewrite this one. So for this equation, r squared theta dot is d theta dt equal to constant. So from here you compare in geometry this small swept area in the very short of time. So that means you can see this equation saying that given the delta t is small, a small amount of the time, r squared d theta is constant. So that means given the same amount of the dt, the swept area must be constant. So say, for example, we're moving from here to here is a dt. and then we move from here to another point, and again from here to here is dt. So the area to be swapped during the same amount of time based upon this one is constant. Got it? So that is which law? Kepler's second law. Got it? So basically here, due to the conservations of the momentum in the tangential directions, that is the meaning of this equation saying no accelerations in tangential directions. That means the conservation of the momentum in that directions. Due to that conservation, then we have this one in geometry. Explanation in geometry simply is this. Okay. And in an orbit, if this is an Earth, if this is satellite, in an elliptic orbit, that is the most of the time the orbit looks like. In an elliptic orbit, the velocity is changing along the orbit. It's not constant. And unless you are in the circular orbit, here I'm kind of chatting, okay? And later we will have an equation. You just listen. In a circular orbit, for example, in the orbit of synchronizing the, how to say that word? Geo constant. Basically, the satellite is this. We can define the satellite is moving along with the rotation of the Earth. So
geostationary? Geostationary?
Okay, thank you. So which means with respect to the Earth, the people on the Earth, you can feel the satellite basically fixed on your top. And for that kind of example, then that kind of orbit is in circular orbit. In the circular orbit, then that is the only situations the velocity is constant. But most of the time in non-circular orbits, the velocity is changing. Okay, so that means during the same amount of the time, the swept area is the same, but the shape will be the same. Okay. So that is the what we can get best out of these equations. And again, this equation is very is fundamental to many things, and those one is the best one we can deduce from that single equation. Seems not very much useful, right? To solve for this equation, definitely we can use we can apply the numerical integrations to do many things, but we don't have to because we do have a very much analytical method for doing this. So the next portions will be how to best utilize that equation, and to explain, I just expressed it. And three constants: linear momentum is constant, and angular momentum is constant. I just expressed here. Linear momentum is constant, angular momentum is constant, and then mechanical energy is constant. Right? In any orbit, the three things should be constant. So that's the reason why the satellites, or if we want to rendezvous, for example, International Space Station. Anyone went to the lectures by the directors yesterday afternoon at the 2:52? Not anyone? So it's a free pizza, right? And many times to send the logistics supplies to the ISS, International Space Stations, they launch the cargoes, and then to the approximate orbits, they need to do fine tuning, and then to chase and to meet the space station. So basically, they keep changing their docking orbit. So, for example, they launch to here, then they begin to do the maneuvering, and then eventually to meet here. So again, this is, for example, this is called the orbit 1, this is called the orbit 2, and then here maybe we have orbit 3. Each orbit has his own fingerprints, which means has his own ID. What kind of the IDs we're given to orbit? Three things: linear momentum, angular momentum, and mechanical energy. In particular, mechanical energy, of each orbit define his locations. So, for example, if you want to switch from one orbit to another orbit, you need to change the mechanical energy of the two-body system. So that means for satellites, you need to have the fuel on his own to allow him to change his relation between the Earth and at that moment. Got the feeling? Okay, so for this one, that one we will gradually kick into. Okay, so I would say today we stop here, and because that one we do need kind of continuous discussion for deriving these three quantities, and that kind of involves derivations, but it's worth it. Okay.